Okay, so before starting in today's and tomorrow's talk, I'm going to introduce kernel method, which has been one of the major field in machine learning, for these, 20 years, I think, maybe more than 20 years already. But before going into the main content of my talk, I want to give a brief introduction of my institute. So our institute has a history of 75 years, and this year is actually their 75th anniversary, and we had a very big event. Our institute is specialized in statistical science. So we have roughly 45 faculty members, and all of them are working on some aspect of statistics, including theory, method, and applications. And our institute doesn't belong to any university, but there are such institutions in Japan. Well, there are 17 such institutions, and one of the missions is to promote inter-university collaboration in respective field. And we also have a PhD course, and officially speaking, this is an independent graduate university, but all of the faculty are co-affiliated to the graduate university, and we have 35 students. So you may notice that the number of students is less than the number of faculty, so their education is very customized to each student. And we are located in Tachikawa City. It's a western suburb of Tokyo. We have a very nice view of Mount Fuji from our institute. And we have some grants for visiting students from overseas. So if you are interested in visiting to Tokyo or our institute, please contact me. Okay, so I skipped this one. You may find some YouTube video which I made for some congress. But anyway, I come back to the main content. Okay, so maybe you have heard about kernel method, and this is, in a single sentence, kernel method is a nonlinear method for data analysis. And developed since 1990s, and the origin of the kernel method was a support vector machine proposed by this guy, Professor Bachnik. And their first paper appeared in 1992, and around 2000, their kernel method have been very well developed as a major tool of machine learning, and still many people are using kernel method. And one nice property of the kernel method, as I already said, that are very suitable for extracting nonlinear features of the data. I'm going into the details from now on. And also, it's very easy to applicable to the non-vector data like graphs, strings, sometimes probability distributions. So here's the goal of my lecture of these 2 days. So the time is very limited. So I would like to give you some basic ideas of kernel method mainly. And one is a mathematical aspect. The other is a typical example. And in today's talk, I'm going to talk about 2 examples: kernel ridge regression, maybe 3: kernel ridge regression and kernel PCA. And also, I will spend some time on the support vector machine, which is our most important, the most popular method in the kernel field. And the next topic is probably tomorrow's topic. I'm going to talk about more recent development. One point is that how to handle very large data like medium. So currently the deep learning is very well popular in machine learning field. One of the strong advantages of deep learning is that it's easy to handle very big data like media. And the kernel method is said to be, well, a little bit difficult to handle such very large data. But recently, the people have tried to develop a method for very large data, and I would like to introduce such directions. And also, at the end of my talk, I will talk about the application to structured data like graph or strings, which are not formulated as vectors, but have some structure. And also, if time allows, I'm going to talk about the kernel mean embedding, which handles the probability distributions like data. Okay, here's the outline, but I skipped this. Well, I already showed the content. Okay, I would like to start with a very basic question. What is data analysis? And this is Wikipedia's definition. I don't recommend you to make a copy from Wikipedia for many things, but this definition is, well, I believe that this is a very nice definition. And Wikipedia says that data analysis of data is a process of inspecting, cleaning, transforming, and modeling data with the goal of highlighting useful information, suggesting conclusion that supporting decision making. Yeah, that's very formulated definition of data analysis. And the kernel method, focuses on some specific aspect of data analysis as I'm going to talk about. So I said in the beginning of my talk, the kernel method is nonlinear data analysis in one sentence. Let's consider then what is linear data analysis, not nonlinear data analysis, but let's start with the linear data analysis. So in many cases, our data is given by as a table of numbers like Excel file, right? And mathematically, we can write the Excel file in the form of matrix. This is very popular, right? And in data analysis, we apply some method of linear, algebra. For example, you know that the principal component analysis does eigendecomposition, and the correlation is also the manipulation of the matrix. And the linear regression is, we have two data, and we make a covariance matrix and apply the inverse of the covariance matrix, and so on. So the linear algebra, in linear data analysis, the data is formulated in terms of matrix, and the linear algebra is a mathematical tool to handle the data. But such classical method of data analysis may fail in some cases, as perhaps most of you are familiar with that. Look at this data. It is unlikely that looking at this data, we want to use linear regression, right? It fails to capture the decreasing and increasing behavior with this data. This is one example. I show you another example. This is a problem of classification. I will come back to this later. So I will explain a little bit detail about this data. This data is the real world data. This is the data of average sea level of some country, Netherlands. And surprisingly, they take the data from 1860. So this is a very historical data, ranging over 100 years. And this is sea level, and perhaps there is a nonlinearity here, but it's not clear what to handle this data. I will come back to this data later. I show you another example. This is binary classification. We want to separate the regions into the blue class and the red class. And it's stupid, obviously, that we use linear separation, right? It's impossible to separate the two classes with a linear line. Obviously impossible. However, we can do some, well, we can apply some mapping from, this is two-dimensional data. But we map simply this data into three-dimensional data. We can apply the linear hyperplane to separate these two classes. Well, it may not be very clear, but this nonlinear transform is made by the quadratic function, x1 square, x2 square, and x1 times x2. With this very simple nonlinear mapping from two-dimensional to three-dimensional space, we can separate these two classes. Well, there's the fancy YouTube video to look at this mapping very closely, so I can show you the movie. Some fancy guy made this movie. Oh, here's some, sorry, this is an ad. Okay, I can skip the ad. So this is slide, sorry, I need to, yeah, just a moment. No. Just a moment, no, sorry, this works. Okay, sorry. Yeah, I clicked. Takes time, sorry. Yeah. So the data is slightly different, but the inner part is blue. Well, this is very vague, but the outer part is red, and we want to separate two regions. And here is a mapping I described in the equation, but actually the two-dimensional data is blown up to the three-dimensional space. And it's easy to separate the inner part and the outer part, right? This is what is done in the equation in the previous slide. And in the two-dimensional space, this is a nonlinear separating circle. In three-dimensional space, that's just a hyperplane. But in two-dimensional space, that's nonlinear. That's in this case, that's just circle. Okay, I come back to my slide. In this way, in some cases, nonlinear transform helps to simplify the problem. In the original space, we need to work with very complicated. We may need to work on very complicated separating curve, but in the high-dimensional space, the separating curve may become just a plane, the linear object. Well, so let's look back at Wikipedia's definition of data analysis. So it says that data analysis is a process of inspecting, cleaning, transforming, and modeling data with blah, blah, blah. But the kernel method focuses on this transforming part of the data analysis. And I show some example that nonlinear transform helps. And the kernel method actually gives a very systematic way of transforming data into very high-dimensional feature space. And the purpose is to extract nonlinearity or higher-order moments of the data. And I talked about the linear and the nonlinear, but we can apply the kernel method to the non-vector data. In that case, linear and nonlinear doesn't make sense because the original space is already not linear space. In that case, we can map the data, non-vector data, to vectors. That is one of the strong points of the kernel method. Okay. Maybe I can make pointer. Okay. So you may think that, okay, this is well, the error of the deep learning. So why kernel? Okay, I can show you some examples that the kernel method, in some cases, outperforms deep learning. So here's an example of the real data analysis. This is our data of the number of malaria patients, basically per population. And so the original data is taken, where the number of the patients is taken is a very broad area like city or town. But we want to make a more closer intensity map using some other information as covariate. And here's the result of the kernel-based method. And I skipped every detail of the model, but from the original data with some information given by some the remote sensing data, we can give a very detailed frequency map of malaria disease. And we do the similar thing by neural network. For neural network, we divide the training data and the validation data randomly to tune the hyperparameter of the neural network. And with 3 random choices, the resulting the frequency map are quite different. So this is caused by the very large capacity of deep learning. Yeah, it's true that the large capacity of the deep learning is very good and advantageous for some problem like the image classification with very huge data set. However, in this case, this is actually not completely supervised problem, but we have only the very data of very supervised data with very low resolution, and we want to make a very high resolution map. And in this case, we recognize that the neural network is too flexible, have too many complexity to tackle with this data. And this is one example that the deep learning is not necessarily a universally nice method. Okay, so excuse me. I'd like to come back to the basic ideas of kernel method. So as I show you through this example and in the previous example, there are some nonlinear transform seems to work for nonlinear data analysis. And let's look at this idea. Yeah, as in the previous case of the mapping from 2D to 3D, it is always true that we can extract some nonlinear features by expanding the data with square and third degree or fourth degree and so on. And this is, well, very classical method to extract a nonlinear information with the data, and it's still useful. However, here's a very serious computational issue. Imagine that our data is very high dimensional, like 10,000 dimensional data. That's very common in the current data. In that case, if we want to extract all the second order movement of the data, we need to handle the 15 million dimensional data. And with the current supercomputer, it's impossible to handle the 15 million dimensional matrix. The eigendecomposition or matrix inversion is impossible. So we need a cleverer way to tackle with this type of, well, especially the high-dimensional data. And the kernel method is one of the strong methods to tackle with very high dimensionality of the data to extract the nonlinearity. Okay. So here is a big picture of the kernel method. So we have an original data space. It may be very the 10,000 dimensional data. And we apply some nonlinear mapping to map the original data to feature vectors. We call the mapped data feature vectors in kernel method. And the space after the mapping is called feature space. And as I explain from now on, this feature space can be infinite dimensional. And it is, well, actually the function space. And in kernel method, after mapping the data, we simply apply some linear method to this feature, to these feature vectors. That is the basic idea and the picture of kernel methods. So by this, the feature map is typically nonlinear mapping, and we can extract the various nonlinear information of the original data by this feature map. And another important point about the kernel method is that the inner product of this feature space is easily computable. And this is very important in many data analysis. In many data analysis methods of data analysis, computing inner product is the most essential part to make the method applicable. So the computation of the inner product, the easiness of the computation, the computing the inner product is essential part of nonlinear data analysis. Okay. So the question is how to prepare this feature mapping and the feature space, and also in the product mathematically. So for this purpose, we use positive definite kernel. This is our the kernel with some special property connected to the inner product or computation with the inner product. So here's some mathematical definition. Let's look at this definition. So simply speaking, the positive definite kernel represents inner product. So we have two arguments. So omega is some space. Well, basically omega represents this original space, data space. So that can be Euclidean space, but can be arbitrary in fact. So we have two arguments of omega, or Euclidean space, if you want to consider this in Euclidean space. And one property is symmetric, where the inner product should be symmetric. So the symmetricity is required. And the second point is positive definiteness. So we prepare an arbitrary number of points in the original space, data maybe, and we compute this matrix, xi and xj is plugged in the ith row and jth column of this matrix. And this type of, this matrix should be positive semi-definite. That is the second requirement of positive definite kernel. Or, this is sometimes called non-negative definite. The meaning is that if you take the quadratic form, preparing the scala C1 through Cn, and consider this type of quadratic form. And this should be always non-negative. That's our meaning of positive semi-definite or negative definite. Okay? And this type of matrix is called graph matrix in this field. So the requirement is symmetricity and the positive definiteness or semi-definiteness of graph matrix. And as we can see, these two properties are very much connected to the inner product. Well, before explaining that, I will show some examples of positive definite kernels on Euclidean space. The simplest positive definite kernel is the standard Euclidean inner product. You can see that this is symmetric. And if you take the inner product, if you consider the quadratic form for xi and xj, we can easily see that it's a positive semi-definite. I will show the proof in a more general case in the next slide. And the less trivial examples are Gaussian kernel and Laplace kernel. Gaussian kernel is named in this way, the Gaussian, because this is similar to the density function of the Gaussian distribution. And this is called Laplace kernel. This uses L1 node instead of the 2 node. And another famous example, the popular example in the machine learning field, is the polynomial kernel. Polynomial kernel is the polynomial function of x and y, and that is also sometimes used. And Gaussian kernel takes this type of shape, like Gaussian density function. But Laplace kernel, because of this L1 node, there is a singularity at the origin. This is, clear difference between these two kernels. Okay. Actually, it's not very straightforward to confirm the positive definiteness of these kernels from the application of the definition, but I skipped that part. That's a little bit involved. Okay. First, as I said that Euclidean inner product is positive kernel. I'd like to show the proof, but with a slightly more general case. We can see that the inner product gives a positive definiteness. Let's look at this proposition. So consider that we have some vector space H with inner product. Can be any vector space. And let's consider the mapping from the data space, original space, to the feature space. And define the kernel K as the inner product of the mapping of these 2 points, x and y. This is definition here. And if we define K in this way, using the inner product, then this K satisfies the positive definiteness. This is positive definite kernel. And Euclidean inner product is one example. You don't need any mapping. The original x and y can make an inner product. And this is positive. Okay, let's look at the proof. This is perhaps the only proof in my talk. But let's look at the proof. A little bit of math. So symmetricity is straightforward, right? The inner product is always symmetric. So you can swap x and y, then it takes the same value. And the non-trivial thing is a positive definite property, or non-negative definite property. And to prove this, we prepare the scalar Ci through Cn, and want to prove that, I see. I forget about phi, sorry. This should be phi xi and phi xj. But sorry. Let's consider this one, phi xi and phi xj. And we want to confirm this is non-negative, right? This is the definition of positive definiteness. Here, we need to recall what is inner product. We say that we assume that we have some inner product in the vector space. Do you remember what is inner product? This is well, the linear algebra, but let's recall this. There are three conditions of inner product. Symmetricity, that's, well, perhaps you know. And linearity. If we multiply scalar to the vector x and it takes the inner product, then the scalar multiplication of the inner product appears. And if we add two vectors, the inner product is decomposed into addition, right? This is linearity. And another important thing is positivity. If we consider the norm, the squared norm, in this way, this is the definition of the squared norm in the space of inner product space. And this should be non-negative. And this norm is zero if and only if the vector is zero. This is a positivity. Yes?
Okay, so why the positive definite is very important. What about the negative definite? I don't know how it can be interpretable.
So negative definite is, well, basically this is the opposite direction, the negative. And in that case, the norm may be negative. Negative definiteness requires that norm is always negative. That's a little bit counterintuitive. So usually, if we talk about the inner product or norm based on inner product, we require the positive definiteness. Length should be positive. That's a very natural intuition, right?
And so if we go back to the slide number 15, and I think data space and it try to map from the filter space, right? And if we are using the positive definite, this means that it's going to like the I think same thing like the first quadrant, like the positive, and I am wondering that if you are using the positive definite and how it's interpretable to the data like the filter map. I don't know how to set the question.
So basically, we want to do some linear data analysis on this space. And if the norm of a vector is zero or negative, that causes us many problems, I think. If you know, for example, linear regression, we want to take the inverse of the covariance matrix. But if that basically requires that the covariance matrix is not singular. And basically that should be positive definite. Covariance matrix is always positive definite, right? And that is required on this space, even after fancy linear.
Makes sense.
Yeah, that is a requirement of the positive definiteness. So this is quite similar to the covariance matrix after of the nonlinear map. So simply consider that the covariance matrix should be positive definite after transforming data. Okay, thank you. So that this is, well, somehow they're rephrasing that fact that we have an inner product which should satisfy the positive definiteness as a definition, standard definition of the product. Then by this transform from the original space to the feature space, we have a positive definite matrix. Okay. I recapture this definition of inner product and apply this definition to expand, not expand, calculate this inner product, this quadratic form. Then the scalar out of the inner product can be inserted in the inner product using the second property, linearity. And we have summation over I and j, and intentionally ci is coupled to xi and cj is coupled to xj. And apply the second property of linearity of inner product. Then we can insert the summation into the inner product. Okay, this is linearity of inner product. And you may notice that the first part and the second part are completely identical. The index is different, but the summation over ci, xi, cj, xj are identical, right? So this is simply the squared norm of this summation. And by the positivity of inner product, this should be always non-negative. This is a definition of the positive definition. Yes. Or, yeah. So the matrix, you mean the matrix made by xi, xj? K of xi, xj, sorry, this is wrong. This is phi xi and phi xj, sorry. And yes. Yeah, here I confirm that this matrix is non-negative definite. Yeah. Is that okay? Yeah. Yeah. Yes, so I'm checking that this matrix is non-negative definite. Yes. Sorry, could you use microphone?
Why do we need positive definite properties for the kernel?
That's probably the same question. His question. We want to make some linear analysis to this space, and positive definiteness are required that some sort of covariance matrix are positive. And if you learn the classical linear, the classical statistical method, then you may notice that in many places, the positive definiteness of covariance matrix are used in developing the method or theory. So the positive definiteness of this space is very important or essential in developing or in applying the linear data analysis method on this space. That is why we are requiring that after transforming the data in this space, we require the positive definiteness of the inner product.
So I'm not quite sure if I'm right or wrong. So for the kernel method, if we would like to positive definite property, does it mean we would like to transform the data into the feature space that is have a convex shape like? Is it correct? Because
in the case of support vector machine and in some other method, it's equivalent to, that's true that the convex property or the quadratic function appears because of this positiveness. Otherwise, we cannot consider the minimum point of the objective function. Yeah, that's basically equivalent.
thank you.
Okay. So I said that if we have a mapping from the original space to the inner product space, then the inner product on this space is necessarily positive definite. Well, we can actually prove under some sort of converse of this fact. Let's start from the positive definite kernel. Then we can implicitly construct some vector space, which is a feature space, and inner product of that space, so that the mapping, well, I haven't included the mapping here, but the mapping, mapping gives a feature map. And I skipped the details of the mathematical fact, but one important property of the feature space is that the feature space is actually the function space of omega. Omega is the original space. So we are considering the feature space as a vector space, but at the same time, feature space is a function space of this original data space. And another important property is this one, the reproducing property. Reproducing property is a very, in some sense, strange property. Let's consider arbitrary function or vector in this function space, and take the inner product of this function and a special type of function, k dot x. K dot x means that we fix x, and then with fixed x we can consider this one to be a function of the first argument. So this is again a function of the first argument. And as such a function, let's consider this inner product. Then the inner product is equal to the function value of f of x. This is a little bit strange property. The function value is given by the inner product of this special type of function. And this is called reproducing property, and this is, used in developing the many kernel methods. And owing to this property, this vector space or function space is called the reproducing kernel Hilbert space. So Hilbert space is, you can simply consider Hilbert space as just a vector space with inner product. And more rigorously, we need some, the property, additional property mathematically, but we are not going to use that property. Simply consider Hilbert space as a vector space with inner product. That's fine in my talk. Okay? Yeah. Sorry? Sorry, this is a typo. HK. This should be H sub K, sorry. Yeah, this the first item skip k, but this should be hk. Okay. So I'll let you talk about the mathematical aspect of the Kernel method. But I'm going to explain how we can use these mathematical apparatus to data analysis. Well, we want to use, okay, let's say that we have a positive definite kernel like Gaussian kernel. And we want to define some nonlinear transform of the original data to feature space. And the feature space is given by the function space reproducing kernel given space, which I showed in the construction mathematical as I showed the mathematical construction in the previous slide. And in kernel method, we always define this feature mapping in this way. Let's say that we have original data, and the feature mapping is given by this special function. This is a vector in the hk, but at the same time, this is a function, right? Or the first argument. Second argument is fixed as the data point x. And we always use this feature map in the kernel method. Okay? And let's look back at this reproducing property. This is a very interesting, strange property. And let's plug k dot y to f. Then we have, by this definition, phi of x, that gives the inner product phi of x and phi of y. Let's plug k dot y to f in the previous reproducing property. And then the reproducing property tells that this inner product of this feature mapping is equal to the function value of k of x and y. Plug this way. Then we have this relation of the inner product. And this property is the most important and the most useful in kernel method. And it is often called a kernel trick. The reason that this is called a trick is that we are using very abstract feature space constructed by positive definite kernel. This is basically implicitly given by the positive definite kernel. And we define the feature mapping this way. And we don't know much about what is actually the feature space and what is this may be a very large space like infinite dimensional space. However, the inner product between these two mapping feature vectors is simply given by the evaluation of the kernel function like Gaussian kernel. So as I showed in some slides, that in many data analysis, computation of the inner product is the essential part in developing the method. And this said that even if we don't know much about what is phi and what is this inner product, the value of the inner product can be simply computable by computation of the kernel values. So by this kernel trick, we have a way of computing inner product in a simple way. Okay? So in the case of data analysis, we have a bunch of data, x1 through xn. And let's take the feature vectors for all the data points. And we have, phi is always phi always means a feature map, and this is phi of x1 through phi of xn. As a function, this is k dot x1 through k dot xn. They are the vectors, feature vectors we want to which we want to apply some data analysis method. And the kernel trick implies that the inner product of the feature vector is simply the value of the kernel, like Gaussian kernel, polynomial kernel, Laplace kernel, and so on. And so in kernel method, all we need is this gram matrix. We don't care much about these feature mapping in, well, practical application of the kernel method. What we need is gram matrix. And once gram matrices are computed, we can simply do some linear algebra with gram matrices. I will show some examples for that. Okay? Is it okay so far? Okay, I would like to show two examples at first. The first example is kernel ridge regression. This is a kind of linear regression applied to the feature space. First, before going into kernel method, I will review the standard linear regression called ridge regression. So this is basically the linear regression. We have, let's consider scalar output, y, and their vector, or maybe it can be scalar, xi, and we want to consider linear regression like this, just the least square error, right? And if we solve this, we have a linear solution to the linear regression. In ridge regression, we add penalty term given by the squared norm with coefficient lambda. And this is, type of penalty term is often applied when the covariance matrix X transpose X is almost non-invertible or almost non-invertible. This is basically the positive semi-definite, so the eigenvalues are always non-negative, but may contain zero or almost zero eigenvalues. In that case, the solution given by the inversion may be unstable. In that case, people often use this type of L2 penalty and solve ridge regression instead of the standard linear regression. And in practice, we have lambda identity matrix in addition to this covariance matrix, and so the matrix inversion is more stable. Okay? And we shall do this in feature space. Okay, let's consider some kernel. Kernel is given, like Gaussian kernel. And we consider the feature mapping. And do exactly the same thing as standard ridge regression on this feature space. Then let's look at this part. This is a linear regression, linear function of x in the standard space. Instead, we consider the linear function on the feature space. Feature space is denoted by h here. So sometimes denoted by h and sometimes denoted by h sub k. So they are basically the same. Linear functional is given by the inner product between a and x. Instead, we have a feature vector, and let's take the inner product with some vector denoted by f. Okay? And f is taken from the feature space. And in addition to the squared error, we add some penalty, L2 penalty term, and solve this problem. And as well, this norm, perhaps the norm of the original ridge regression is clear. This is just a norm of the vector. And this is also the norm of the vector f. But in fact, this is related to the smoothness of this function. This is vector, but also this is a function. And this gives a solution. And this is related, the square norm is related to the smoothness of this function, but I will explain it in tomorrow's talk. But anyway, we have some the replacement of the standard ridge regression to the kernel space. Well, using the reproducing property, we can rewrite this in terms of nonlinear regression. Well, this is k dot x, I, and if you recall the reproducing property, this inner product is equal to the function value of f of xi, right? This is the reproducing property, the special property of reproducing kernel space. And then, this is some nonlinear function given by f at xi, and this squared error is measuring the difference between the function value of f and observation y as output. So this can be regarded as the objective function of nonlinear regression. And f is a solution. So we have two alternative views to kernel ridge regression. This is standard extension of the ridge regression in this feature space. Alternatively, we can consider it by the reproducing property as nonlinear regression between f of x and y. Okay? And we can actually solve this in this way. I will show the detail in the next slide. The solution is given in this way. I explained the notation. So k is a gram matrix given by input x, and y is a vector consisting of the output. And k of x, the bold k of x, is a vector given by kx x1 through kx xn, x1 through xn of data point, input data point. And basically we have n times n matrix here, and n-dimensional vector in the left-hand side and the right-hand side. And this makes the solution to the nonlinear regression, which is called kernel ridge regression. We require that the gram matrix is always non-negative definite by the definition of positive definite kernel. However, the eigenvalue may be arbitrarily small. Should be non-negative, but arbitrarily small. So this penalty term helps to make this matrix invertible stably. Okay. I explain a little of the math to derive kernel ridge regression. The question is, we have this clear objective function, and we want to solve this one or this one. And the question is how to solve. So we don't know much about this feature space. This may be infinite dimensional. And the solution f must be taken from this Hilbert space, the feature space. that's very abstract, looks very abstract. But in fact, very fortunately, we can reduce this functional problem to finite dimensional problem. This is another advantage of kernel method. We at first look, we may solve the solution. We may give the solution from the infinite dimensional function space. That seems very difficult. But in fact, the solution is given by the linear combination of kernel functions. So this is feature vector, and Ci is the linear combination, the linear coefficient. And we can prove that our solution always takes this simple linear combination of feature vector. Why this happens? So this is a little bit abstract, but any vector can be decomposed into two parts, orthogonal decomposition into the space spanned by the feature vector. This is finite dimensional, n-dimensional space at most, and orthogonal direction to the space spanned by the feature vector. This is always possible by orthogonal decomposition. And the first term is linear combination. Then I use Ci as coefficient and given this form. And if we look at this objective function of kernel regression and plug this decomposed form of f, the second blue part is always orthogonal to feature vector. So this inner product, in this inner product, orthogonal direction should disappear because this is always orthogonal to these vectors. So the inner product of this part is reduced to the simply phi of phi given by the linear combination of finite number of vectors. And we have second term here, the penalty term. By Pythagorean equality, by the orthogonal decomposition, we can consider that we can rewrite the squared error in terms of the sum of the squared error. Right? We are considering the squared moment, this one, but the orthogonal decomposition tells that the squared moment, this one, plus squared moment, this one, gives the squared moment, right? So we can rewrite this term into two parts. And the first term is given by simply the red one. And the second term is given by the first term and second term, the summation of these two squared modes. And we can see that f orthogonal should be 0 by taking minimum. That is the most, if you want to minimum, then we can erase this part. That should always give a smaller part. So as a result, we can always have a solution in this first part. Second part should be 0. And then we have this finite dimensional combination of the feature vectors as a solution. After confirming this fact, we can plug this form to the objective function of the kernel edge regression. And using kernel trick many times, we can derive this objective function. And this is, simply the squared quadratic function of coefficient Ci. And we can solve Ci. This is just a quadratic function. So we can explicitly solve this vector Ci as a solution. And the previous form of the solution is solved in this way. Okay? Okay. I have shown that objective function takes a form of the minimization in the Hilbert space, which may be infinite dimensional. But as a result, we can confirm that the solution takes simply the linear combination of feature vectors which are finite number. This representation of the solution, the finite dimensional representation of the solution, is often called the representer theorem. So solution in original, there must be taken from the infinite dimensional space. But as a result, we can confirm that the solution is given by the linear combination of a finite number of vectors. And what we need is to solve the coefficient to those vectors. The problem can be reduced to the finite dimensional one. This is called the representer theorem, and this is another important ingredient consisting of kernel methods. Okay. So this is the exercise that you can confirm that this objective function can be reduced to the objective function using CI. This is perhaps exercise 2. Okay, here's a result of the application of kernel regression to the sea-level data I showed in the first couple of slides. So we use Gaussian kernel, and the Gaussian kernel has parameter of the boundaries, and I adjust the boundaries in some way. I skipped the details about how to choose it. But by kernel regression, the nonlinear function to express the relation between x, y, and y is estimated in this red curve. So obviously you have a tendency that the first decrease around 1,900. Well, this is a year, and after that gradually increasing. But you may observe that some periodic behavior with dozens of years may be observed. I don't know what is this small perturbation, and nobody knows actually. But by this nonlinear method, we may detect such the minor perturbation behavior or the periodic behavior from this data. Okay. Yes. Oh, sorry. This is actually given by some regions. Sorry, I just took the figure from another talk, so don't neglect this one. We can actually compute the confidence interval. But this is I basically use a Gaussian process approach to compute the confidence. The Bayesian approach. I will not explain in this talk. Okay. So I'm going to talk about second example, kernel PCA. So the first one is supervised program. We have x and y and estimates the nonlinear function to explain the relation between x and 2y. Kernel PCA is the nonlinear extension of PCA. So this is unsupervised program. We want to have a low-dimensional plots of data in an unsupervised way. You may know that the principal component analysis. This is the most basic approach to make a low-dimensional projection of the data. And this is quite useful in many data analyses at the first step. And the basic idea is to, this is just a two-dimensional, maybe high-dimensional. And we want to extract low-dimensional space, 2 or 3-dimensional space, to project the data onto the low-dimensional space. the criterion of obtaining the low-dimensional space is the variance of the data. We want to find the subspace with the largest variance among the 2 or 3-dimensional space. And the first direction is given by the direction to give the largest variance. In the case of PCA, we first subtract the mean to consider the variance and project the data onto the direction of A. So the norm of the A is 1 to make the projection. And consider the variance of this. We already subtract the mean, so we just project the centered data onto the direction of A and solve the minimization problem. Then we have the direction, this direction, as a solution of A. And as you may know, that this minimization problem can be reduced to an I problem. We can simply find the direction to give the minimum I. Sorry, that's completely wrong. This should be maximum. Sorry. Maximum. Sorry. So the largest variance must be detected. This is completely opposite. This should be maximum. So the maximum eigendirection gives a solution. And the kernel PCA does the same thing on the feature space. Okay, let's look at this one. So instead of the original data, we take the feature vector, phi of x, after providing some kernel. And then, we can consider the mean vector on the feature space. This is simply given by the mean of the feature vectors. And project this centered feature vectors onto the direction of f. F is vector in the feature space. And as in the standard PCA, we restrict the norm of f as 1. And this is again maximum. This should be maximum. So this should be maximum. And consider the maximum direction and the direction to give the maximum variance. This is completely standard PCA. And this is again the optimization problem on the Hilbert space or the function space, feature space. However, as in the previous ridge regression case, we can reduce the problem to the finite dimensional one. This is again the representer theorem. In fact, I skipped the details. We can find the solution as a linear combination of centered feature vectors. What we need to solve is just a linear coefficient, n linear coefficient Ci for kernel PCA. And this can be confirmed by using exactly the same idea. We can decompose f into the linear combination part and the orthogonal part, and then the orthogonal part should be 0 as a solution. We can take 0 as a solution. Well, this is also the exercise. After confirming that the solution is given by linear combination, we can plug this solution form to the objective function f, this part. And this can be written in some way using grammatics. And actually, this is given by the so-called centered grammatics. This is the definition. And this is part of standard grammatics. And we subtract and add some terms, and they basically adjust the mean value of the feature vector. We call it centered analysis. Anyway, the problem can be reduced to eigenproblem again to solve the coefficient C. I skipped the details, but the solution of the kernel PCA is given by the eigen decomposition of this centered matrix and the principal component of xi. P's principal component of xi is given by the eigenvector and multiply the square root of the eigenvalues. Yes?
Is the minimum supposed to be maximum too, or is this?
Yes, this is maximum. Oh, sorry, I always use minimum, but so this should be maximum. Thank you. I fix the typos for the final version. Yeah, I think I use this type of slide many times, but I always use minimum instead of maximum. Sorry. Okay, so the kernel PCA is a kind of dimension reduction. What we are doing is that map the data into some feature space and takes the best two-dimensional plot on the feature space. That is what is done in kernel PCA. I show some examples. This is a very famous data from UCI record. Yeah. Which one? Sorry? F gives a direction, eigendirection. And after taking eigendirection, we project the feature vector on that direction. And that gives a coordinate value of that vector, right, as in the standard PCA. Sorry. F is actually the maximizer. Yeah, F is the eigenvector to give the maximum eigenvalue. And that gives the direction or axis in the feature space. And we plot the data on the axis. And the projection is computed if we can compute the inner product. So, and we have a way of computing inner product by kernel tree. So we can compute everything. Okay, I show some examples. This is our wine data, and this has our 178. Sorry, I deleted data here. But 178 points. 13-dimensional data, which consists of the 13 chemical measurements of 3 types of wine. This is a real wine data, and this is an Italian wine we taken from the 3 different places. So we are expecting that 3 different cultivars have different chemical properties because the taste is usually different. And by making our 2-dimensional plots, if we can see 3 classes, that probably that is a reasonable 2-dimensional plot. And we know that there are 3 classes, but we are not. The kernel PCA or PCA is a unsupervised method, so we are not using the class data. So in fact, the plots are like this. So left one is the linear PCA, and the right one is the kernel PCA. Well, may not be very different from this figure. I use a Gaussian kernel for making this plot. However, if we choose the bandwidth parameter of the Gaussian kernel in an appropriate way, we may observe very clear three classes in this way. However, we need to be careful. This is a form of Gaussian kernel, and this sigma is the bandwidth parameter, the hyperparameter of Gaussian. If we change this sigma in a various ways, taking various values, the results are quite different. This small sigma detects three classes very clearly, but the plot is like three needles. And this may look more clustered in some sense, group, but the difference of three classes or the borders are a little bit vague. And if we take a very large value of sigma, the result is not very different from the standard classical linear PCA. So the choice of sigma is very important to the result. And because this is unsupervised problem, like PCA, we cannot say that which is correct. Everything, all the results are correct. But if you want to see the clear three classes, then this may be correct. But the shape of the data may look a little strange. So the choice of sigma is very important to the result. But I'm going to talk about the choice of sigma briefly later. Okay, I want to summarize the common property of kernel methods. I showed two examples, kernel ridge regression and the kernel PCA. And there are common properties in developing the method. First thing is that we are applying linear methods to features on the feature space. So this is sometimes called kernelization of the linear method. And we have feature vectors in this way. And there are important points that we can always compute the inner product by evaluation of kernel values. And this is called kernel tree, as I explained. And the third important point is that in most of the kernel methods, we can find the solution as a linear combination of the finite number of feature vectors. This reduces the infinite dimensional problem to finite dimensional one. And this is called the representer theorem. This makes an essential, useful point in the kernel method. And after taking this form, usually everything in the objective function can be written by graph matrix, and we can solve it. And after representing everything in terms of graph matrix, we don't care about what is original space, and the algebra on the graph matrix suffice to derive the solution. So as I explained in tomorrow's talk, we can apply this idea to non-vectorial data like graph or strings. Okay. Well, I'm going to talk a brief comment about the choice of kernel. As I showed in the example of kernel PCA, the choice of kernel is very important to get a good performance of the kernel method. And for example, the Gaussian kernel has this variance parameter, or sometimes called bandwidth parameter in Gaussian kernel. And we want to choose this parameter appropriately. So I showed an example of kernel ridge regression, and perhaps tomorrow I'm going to talk about support vector machine. In the case of such supervised learning, the cross-validation is a standard method to choose this hyperparameter sigma. So we prepare validation data and check the performance of the validation data to choose sigma. That's a reasonable way to. And in the case of unsupervised learning like kernel PCA, there is no such validation data. So unfortunately, in this case, we don't have any general method to choose a hyperparameter. And we need some outer criterion to choose a hyperparameter. For example, the dimension reduction is sometimes used as a pre-processing of the next stage, like the supervised problem. And in that case, the final goal of supervised problem can give the criterion of choosing the hyperparameter. That's one thing. And another, well, I'm not going into the detail, but we can sometimes use some sort of Bayesian framework to choose hyperparameter. I'm not explaining this one. And another way is to use some background knowledge about the problem. The kernel, the choice of kernel strongly influences on the function as a solution, like kernel regression. In that case, the bandwidth parameter determines the smoothness of the function. So if we have some knowledge about the roughness or smoothness of the solution, then we can use such the background knowledge to choose a kernel. That's another thing. And another interesting idea to choose kernel is instead of choosing kernel, let's learn kernel. This is called multiple kernel learning. In this method, people consider the linear combination of many kernels, like different bandwidth parameter or different kernel, like Gaussian, polynomial, and so on. And it takes a convex combination. Convex may not be a well, they should be non-negative, but the summation may not be. And okay, anyway, they consider the combination of kernels and optimize these coefficients in some objective function, like support vector machine or kernel regression. And this type of method have been developed also. But the difficult point is that computationally it's much more expensive than the standard support vector machine or kernel regression. And we have a trade-off of computational cost and performance gain. In some problems, by optimizing the kernels in this way, that we have a big gain. But in some problems, the computationally much harder, but the gain is very limited. That may happen. So the people sometimes just apply just a summation, not optimizing the coefficients. That's also used in some problems. If you are interested in this type of multiple kernel learning, there is some nice review paper, so you can look at this one. Okay, I think I'm running out of time, so I will explain the support vector machine tomorrow. Yeah. Okay, so any questions so far?
I just want to check my intuition here. So does the representer theorem directly follow from the fact that the linear combination are dense in H?
Yeah, so
the second property of the Aronszajn theorem says that the set of the linear combination of
yeah, so the representer theorem tells us solution is given in this form.
So that does follow from the fact that the set of such linear combination is dense in the Hilbert space. So you can approximate any solution arbitrarily close by the
That's not exactly true. It's true that the linear combinations span the space basically, but this one tells that with finite number of vectors, the solution of the objective function is always found in this form. So this is not related to the other places or the denseness of the linear combination. But given the n data points, we can reduce a problem to the n-dimensional problem.
Thank you.
Well, may not be unique. In some cases, for example, in the kernel ridge regression, this form, the solution is always takes this form. But the CI may not be unique.
I have maybe very basic question. So I got lost like near the very beginning when you start to formulate the kernel regression, because I'm not familiar with the inner product notation. So I'm kind of confused. What exactly do you do when you apply like the inner product of f and the phi x? In next slide, yeah. How do you change from first line to the second line
Okay,
here?
so you understand that this is the inner product between A and X.
Yeah.
Okay. And this is simply the inner product of two vectors.
Right.
And this bracket represents the inner product. The meaning of this bracket is the inner product between f and this vector, phi of x.
And f is a function, right?
F is a function, but function is vector. So simply consider this is vector in this representation, in this formulation. And this is vector, and this is also a feature vector. So we are taking our inner product of two vectors.
And this is now in the maps, the feature space, not in the original space.
Right, this is in the feature space, not the original space.
So f at this point we don't know what form f will take yet.
Yeah, we don't know about it. F is taken from abstract feature space. Yeah, so in this form we just express our objective in our abstract form.
So in the end, like when you obtain the solution to this problem, is f like a function that transforms from the original space, or do you enter like the transform the phi x into f?
This is perhaps an important point given by the reproducible property. This is a vector and inner product, but this inner product is equal to the function value. This is a vector view, and this is function view. So as a result, this inner product is reduced to the function value of f at xi. This is our interesting point of problems. We can view, we have two views, vector view and the function view. And interplaying with these two views, we can derive the nonlinear function as a solution.
I just find it surprising that those two quantities are equal, because
this is a little surprising.
The first one is in the feature space, but the second one is in the original.
This is the function value. So at first look, this may not be so related, but actually in our interesting point of reproducing kernel Hilbert space, that's a very special property. The inner product gives a function value. That's a kind of surprising vector space.
Thank you.
Yeah.
Please
Okay.
stop now because I have a little bit left.
Maybe one quick question.
Yeah.
So, I mean, in the past few days, we learned a lot about deep learning.
Okay.
So, can you give us a quick